Hey, what's up, everyone? How's everyone's Friday going? That's good.
It's going great. These stocks are going really well.
Going great. What's going really well?
These stocks.
The stocks. Oh, really? You invest in some GameStop or some Dogecoin or something?
Yeah. Doggy coin to the moon.
Glad that's working out for you, man. I had a couple people trying to get me to invest in Dogecoin, and I'm like, I don't know, man.
You should do it. I guarantee you'll make some money off of it.
Yeah, I feel like that's gonna get shut down really quickly.
It actually did.
Can't let the plebs make any money off this, man.
It actually did get shut down, but people are trying to hold their money out until they open it back up.
Yeah, that's the thing. Like it's gonna go up, but like you don't know how long. But I don't know. I mean that'd be fun. But yeah, that's cool that some of you guys made some money. That's good to hear.
Oh, Grant, don't sell. You gotta hold, bro. Don't sell. Oh man. Don't sell. Don't sell.
See, I'm just worried I'm gonna like buy stocks, and if I don't keep an eye on it like at all times, like I'm gonna lose a bunch of money. Like it's just gonna like bottom out while I'm like teaching lecture or something. I don't know. We'll see. Maybe I'll get in on the game. Who knows? Alrighty. So today we're gonna finish up talking about the cross product and possibly start talking about vectors if we got, or vectors, planes if we got time. So it puts us a teensy bit behind the schedule on the syllabus, but that's okay because I definitely don't plan on spending even like one entire day on one of the sections that it allots 2 days. And this always happens at the beginning of the semester. I always feel like I'm playing catch up, and then by the end of the semester, I feel like I'm stretching everything out and like end up having extra time at the end. So it's pretty common. But yeah, so don't freak out too much if we're not exactly where the syllabus says. 12.3 due to, is 12.3 due today? Yes, 12.3 was, should be. Let me make sure.
Yeah, it is.
Yeah. 12.3 is due today, the learning curve. Yeah. Correct. Yes. Okay.
I have a question on the homework real quick.
Mm-hmm.
If I can ask. So you know how you had like vector u and then the parallel lines and then sub vector v?
Yes.
What's like the equivalent? Because in the homework it says like proj, like sub u, like v, or like.
Yeah, okay. I guess that's weird that it's doing different notation, but yeah, okay. So love to see it. So u parallel sub v is the projection of u onto v. So like in both cases,
Okay.
the thing in the subscript is the thing in the bottom is the thing like the ground, the thing being projected onto. And that's how I remember it with the formulas, because the stuff on the ground is also the stuff in the denominator.
That makes sense. Nice.
And then the component you might also see be written as the component of u on v. That's supposed to be a v. But yeah, I don't know if they also use that notation, but the other book used to do that, use the proj and the comp. So that's a little strange seeing this book do that, but you know, I haven't been a big fan of this book. It's been a little, I don't know. I don't like it as much as the other one, but yeah, I didn't realize they use that notation also in because they don't use it in like the text. So that was, but yeah, that's what that is. Okay. So 12.4. So let's continue to look at the cross product. Spent a lot of time yesterday looking at how to actually calculate the cross product. And won't go over it again, but if you have two vectors in R3 and they have to be vectors in R3, otherwise this is not defined. So V is V1, V2, V3, W is W1, W2, W3. We define the cross product, V cross W, and order matters, as we'll see, as the determinant. And we talked about how to calculate these yesterday. So the top row is IJK, which are the standard unit basis vectors. I is 1, 0, 0, J is 0, 1, 0, K is 0, 0, 1. And then the second row is the components of the first vector, V. And the third row is the components of the second vector, W. Okay, so that's how we calculate it, but it does not give any inkling whatsoever as to what is actually going on geometrically with this. And that is the most important piece of the most important aspect of the cross product. Yes, yes, I'll go back. Okay, so what actually is the cross product? So I mentioned before that the cross product, basically, if you have two vectors, two non-zero vectors, U and V, yep. Then the cross product of the two gives you a third vector, which is orthogonal to both of these, both U and V. So U cross V is orthogonal to U, and it's also orthogonal to V. Now, that's only a piece of the puzzle, because, so that doesn't uniquely describe U cross V, right? Because if you have two vectors, so think about your two vectors lying in like the desk, right? So there are two general directions which are orthogonal to any vector parallel to the desk, right? Straight up and straight down. Like those two guys are parallel, but it matters which one in this case. So how do we determine which direction? How do we determine which direction our vector's pointing in, and how do we determine the magnitude of the vector, right? Those are the two things which uniquely describe a vector. So what's the geometric description of the cross product? Right. So to determine the direction of U cross V, we're going to use the right-hand rule again. Except it's going to be a different version of the right-hand rule. And it won't be the last time we'll see the right-hand rule, in fact. So here's how the right-hand rule is gonna work, right? So take your right hand. So you start pointing your fingers in the direction of U. Sorry, let me use V and U and V is fine, whatever. So in the direction of whatever the first So let's talk about U cross V. So in U cross V, use the first vector, right? Order matters. U cross V is not the same as V cross U, but use the first vector. So you start your fingers pointing in the direction of U. So let's use the picture I drew here. And you position your hand so you curl them inwards towards V. So you curl your fingers inwards towards a second vector in the cross product. In this case, that's V. Your thumb points in the direction of the cross product. So let me make sure I can see this. Okay. So in the example, actually, that's a little confusing because I'm backwards. But so you point your fingers in the direction of U. You curl them inwards so they point towards V. If you position your hand correctly so that you can do that, your thumb will be pointing in the direction of U cross V. Notice your thumb is orthogonal, perpendicular to U and perpendicular to V. Your thumb is pointing in the direction of U cross V. Does that make sense? So, for example, or let me mention this. Just this will be a nice shorthand. So we say U, V, U cross V. The order matters here. Forms a right-handed system. So that means you follow the process, right? You start your fingers in the direction of the first guy. You curl them inwards towards the second guy in the set. Your thumb is pointing in the direction of the third guy. That's a right-handed system, right? The order matters here. So V, U, U cross V would not be correct because they would not be, that description would not work there. You would have to actually turn your hand around and we'll see what happens there in a sec. But so for instance, suppose both of these vectors are lie in the plane of the whiteboard, right? Suppose that's U and that's V. So using the right-hand rule, is U cross V going to be pointing into the board or coming out of the board towards you? So into the board away from you, out of the board towards you. Right, so you position your hands. So you go from U to V. Your thumb is pointing into the board. And notice, if I switch it, if I do instead V cross U, now V is the first vector, so I want to start my fingers in the direction of V. Kind of hard to do, but you start your fingers in the direction of V. curl them inwards towards you. Now my thumb is pointing towards me out of the board. Pointing in the exact opposite direction. So the order actually changes the vector. We'll see exactly how in just a second, but that's how you determine the direction of u cross v. Use the right hand rule. Okay, so we have direction down. What about the magnitude of u cross v? Well, turns out the magnitude of u cross v is, this will look familiar, but slightly different. Magnitude of u times magnitude of v times sine of the angle theta between the two. So remember, the dot product of two vectors is magnitude u, magnitude v, cosine of the angle between the two. The magnitude of the cross product is similar, but it's magnitude u, magnitude v, sine of the angle between the two. So one way to remember this, I guess, just so you don't get them mixed up, you probably won't, but remember your, so remember theta lies between 0 and pi, right? Remember the dot product can be negative, right? And cosine of theta can be positive or negative between 0 and pi. However, sine of theta is always positive between 0 and pi. And that makes sense because the magnitude of a vector is always positive as well. So it wouldn't make much sense if the magnitude was a negative thing. So the thing that's always positive, the magnitude of the cross product, is going to involve sine. And then the thing which can be, the thing which is always positive. And the thing which can be negative, the dot product, involves the other one, cosine. Okay. So just to summarize, so I'll use V and W again, just because. So V and W, well, okay, let me. Nah, that's fine. Don't need to spend time on that. Okay, so one thing to notice about this is, so the magnitude of u cross v, magnitude u, magnitude v, sine of theta. So notice, when is the cross product going to be the zero vector? Well, the zero vector is the only vector whose magnitude is 0, right? So whenever this magnitude expression is zero, that's when the cross product is a zero vector. So let's see when that happens. Well, we get the zero vector when either magnitude of v is 0, magnitude of w is 0, or sine of theta is 0. So the cross product is 0 when either, well, if magnitude of v is 0, then obviously v is a 0 vector. If magnitude of w is 0, then obviously W is a 0 vector. But what about when sine of theta is 0? When can that happen? For what values of theta can we get between 0 and pi? Pi is one instance where it's 0. But remember, in the unit circle, the y coordinate is sine of theta, and that happens at either theta equals 0 or theta equals pi. So what does it mean if theta equals 0? Well, your two vectors point in the same direction. The angle between them is 0. If theta equals pi, they point in the opposite direction. In either case, your vectors are scalar multiples of each other. They're parallel. So if your cross product is a 0 vector, that's only going to happen when one of your vectors is 0 or your two vectors are parallel. They point in the same direction or opposite directions. We'll summarize this when we, and the following is part of the following theorem. Okay. So we saw earlier, when you change the order of the cross product, you get a vector pointing in the opposite direction. It turns out you get exactly negative of your original vector when you change the order of the cross product. So W cross V is just negative V cross W. You change the order. Changing the order of your cross product is the same as just taking negative of the original vector. You get the same vector, but it's pointing in the opposite direction. So related to what we just talked about, you take a vector, you cross it with itself, you get the 0 vector. Why is that? Well, because a vector is parallel with itself, right? The angle between V and V is 0. So from what we just said, the magnitude of the cross product is going to be 0, so you're going to get the 0 vector. So V cross V is a 0 vector. And in fact, the only time we get the 0 vector is if V is 0 or W is a scalar multiple of V. Remember, two vectors are scalar multiples and they're parallel, or non-zero scalar multiples. So notice this, it's not mentioned here explicitly, but this contains in it. So lambda could be 0 here, in which case W would also be the 0 vector. So V is a 0 vector, W is a 0 vector, or your two vectors are parallel. They're scalar multiples of each other. That's always going to give you the 0 vector when you take the cross product, and that's the only time that happens. So so similarly to the dot product, we can kind of, if we have a scalar in there, you can kind of move it around however you like in the cross product. So you can multiply the first one by that. You can multiply the second guy by that. You get the same answer. Or you can just pull it out entirely and then take the cross product. Doesn't matter. You can move around scalar multiplication however you like. And then we also have the distributive rule. So the cross product distributes through parentheses, through addition, the same way it does in normal multiplication. So u cross v plus w is the same as u cross v plus u cross w. And then the same thing. If you have that first, if you have the addition first, then it distributes exactly how you would expect. U cross w plus, sorry, v cross w. But notice you have to keep the order the same, right? The stuff on the left of the cross product has to stay on the left, and the stuff on the right has to stay on the right. And number 3? So number 3 is saying, it's telling you when you, so when you can take the cross product to 2 vectors and get the 0 vector. That happens when either one of the 2 vectors is the 0 vector, or the 2 vectors are parallel, scalar multiples of each other. And it also says that's the only time you can take the cross product to 2 vectors and get the 0 vector. So it's saying it's basically saying either one of the 2 is the 0 vector. That could happen. So it says if v is 0, so if lambda could be 0, if lambda is 0, then w is a 0 vector. Or if neither of those is true, then w is some scalar multiple of v, so they're going to be parallel. So that's the only time the cross product is 0. One of the 2 guys is 0, or they're parallel. Okay. And I quickly want to mention sort of a useful fact. It's I, J, and K. They're cross products. So I is 1, 0, 0. It's the vector, the unit vector pointing in the direction of the positive x-axis. J is 0, 1, 0, the unit vector pointing in the direction of the positive y-axis. And K is 0, 0, 1, the unit vector, wow, pointing in the direction of the positive z-axis. Okay, so we know all the axes form right angles with each other. They're all orthogonal. So we know I, J, and K are all orthogonal to each other. K is orthogonal to I and J. They're all mutually orthogonal, right? They all are perpendicular with each other. So it turns out, if we take the cross product of any 2 of them, so for instance, I cross J, the magnitude of that is going to be the magnitude of I times the magnitude of J times sine of, well, we know they're orthogonal, so sine of pi over 2. Well, what's the magnitude of I and J? They're both unit vectors, so by definition, their magnitude is 1 each. So it's 1 times 1 times sine of pi over 2, which is 1. Right? So the magnitude of I cross j is 1, right? We get a unit vector. So we know the magnitude. What's the direction? So do the right-hand rule. Is it pointing in the direction of k or negative k? Well, when you do the right-hand rule, start your fingers in the direction of I, curl them in towards j, fingers pointing up in the direction of k. So we know we get a unit, we get a unit vector pointing in the direction of k, which of course is k, right? That's the unit vector pointing in that direction. And then using the same logic, if you do j cross k, you get a unit vector. And when you do the right-hand rule, your thumb points towards you, which is in the direction of I. So unit vector in the direction of I is, of course, I. And then similarly, k cross I. Start your fingers in the direction of k. A little difficult to do. Curl them in towards I. Fingers pointing in the direction of j. And by the same argument, we know it's a unit vector, so we get j. So I cross j is k, j cross k is I, k cross I is j. So if you kind of go around in that order with the cross product, if you go, let's go around in this order. If you do I cross j, you get k, j cross k, you get I, k cross I, you get j. If you go around in that order, you get the next guy. If you flip them, of course, you get negative of that. So of course, k cross j would be negative j cross k, which is negative I, so on and so forth. But these are nice to remember. Just remember, do the little wheel thing, I, j, then k. If you follow around the wheel, and that's the order you take for the cross product, you do any two in that order, you're going to get the next guy when you take the cross product. So I cross j, you get k, j cross k, you get I, k cross I, you get j. Useful to remember sometimes. But I don't want to dwell on that too long. But one thing I will mention, and you're not going to need to remember exactly what the formula is for this, but one thing to be careful here. Cross product is kind of weird. So normal multiplication, right? If you do like A times B times C, that's the same as A times B times C, right? For numbers A, B, and C. Doesn't matter what order you take the multiplication in. With normal numbers, you get the same answer. Cross products, unfortunately, don't work the same way, right? So if I do I cross, say I cross J, well, what is I cross J? Well, we said that is I cross, whoops. That's how. I cross J is K. So this is I cross K. And I cross K is negative K cross I. So that's negative J. So if we group our parentheses like this, we get negative J. But how about if we do I cross I and then cross J? What do we get? What is I cross I?
Zero.
Right, we get the zero vector. Right, you cross a vector with itself or anything parallel to it, you get the zero vector. And what is zero cross anything? The zero vector. So if you group your parentheses differently, you get a different answer. So that's all I'm going to say about that. The cross product is a little weird in that respect, but that's the main way in which it doesn't work like normal multiplication. Other than, you know, the fact that you switch the order, you get negative at the answer as well. But that's generally not something that pops up too much. But yeah, something to keep in mind. Okay. So cross products also have a relationship to area and volume of certain geometric objects. So suppose we have suppose P is the parallelogram with sides the vectors v and w. So what do I mean by that? So take your vectors v and w, two vectors, and start them at the same spot. All right, and then basically those are two sides of your parallelogram. Well, the opposite sides have to be parallel. And so your other guys here are also copies of v and w. Right. So if you have a parallelogram whose two adjacent sides are the vectors v and w, you consider them vectors in this case. So then the area of this parallelogram is the magnitude of the cross product of v and w. I won't prove this. The book shows this. It's pretty simple, but I want to move along here. So yeah, the area of the parallelogram spanned by the vectors v and w, whose sides are the vectors v and w, is the magnitude of the cross product of v and w. Similarly, if you have a triangle which has two sides, v and w, you only need two of the sides. And in fact, it doesn't matter which two sides you pick. The area of the triangle with sides v and w is 1/2 the magnitude of v cross w. Why is that? Well, that's because, so suppose you have a triangle here. One side is V, one side is W. Notice you could take the sides V and W and complete a parallelogram. Pretend that's a parallelogram. Then notice this triangle, the area of that triangle is half the area of the parallelogram because this is a copy of that guy, right? Because this is W, this vector, this guy is V, and this is obviously they share a side, right? Side, side, side congruency. So you can think of a triangle as half of a parallelogram spanned by V and W. And so the area of that is going to be half.
How do we know which side to do first in the
So that's the thing, it doesn't actually matter which side you choose. You're going to get the same answer, right? Because if you do, like if instead I choose, say, this to be V and this to be W, instead of the other two I chose, then I can still do the same thing, complete the parallelogram, and it's still half the area. So in fact, it doesn't matter which two sides you choose, you're still gonna sort of magically get the same answer. Which is actually kind of interesting, but yeah. Okay. Okay, and then let's do a quick example. Or you know what, let me talk about the scalar triple product and then I will do an example. So now if we go to 3 dimensions, we have an object called a parallelepiped. With edges U, V, and W. And let me show you what that is so I don't confuse everyone with my awful drawing. So this guy here is a parallelepiped, right? It's like a 3-dimensional parallelogram, right? You have 6, it's like a cube, but your faces are parallelograms rather than just squares necessarily. And opposite sides are parallel. But basically your edges are going to be one of 3 vectors. Your U, your V, or your W. Every other edge is a copy of that. Okay, so that's a parallelepiped. So it's a 3-dimensional object. So we can talk about its volume. And it turns out the volume of a parallelepiped with edges U, V, and W is the absolute value of U dot V cross W. And we need to take the absolute value because the dot product, remember, a dot product can be negative. And the reason this could be negative, it depends on the order, right? You could call whichever one you want U, whichever one you want V, whichever one you want W. Depending on the order you take, that could change the sign of this guy. But if you take the absolute value, then that takes care of it. So you could do that, but there's a quicker way to calculate this. And that's basically with determinants. So the scalar triple product so suppose U is U1, U2, U3. Whoops. V is V1, V2, V3. And W is W1, W2, W3. So you could calculate the cross product of V and W and then dot it with U if you like. But you can do this all in one go by just doing a single determinant, right? So you let the top row be the components of the first vector, U. The second row is the components of the second vector, V. And the third row is the components of the third vector, W. So you're just taking the determinant of a 3x3 matrix rather than calculating the cross product and then taking a dot product. And so rather than taking this, doing the U dot V cross W and taking the absolute value, you can just take this determinant and then take the absolute value of what you get. So in other words, this is equal to, for real, come on man, the absolute value, because changing the order of your rows could change the sign. But if you take the absolute value, you're going to get the same answer. U1, U2, U3, V1, V2, V3, W1, W2, W3. So you take that determinant. And then you take the absolute value of that determinant. That's going to give you a number. Take the absolute value of that guy. Does that make sense? Okay, so I'm going to really quickly do one example. This is probably the most important use of this scalar triple product. But consider the following. So a parallelepiped is a three-dimensional object, right? It has a volume. But what happens if all three sides lie in the same plane, right? Suppose this is U, this is V, and this is W. Suppose they all lie in the XY plane, right? If you form the parallelepiped whose edges are parallel to this, you're going to get a flat object, right? It's going to lie entirely in the XY plane. So we say three vectors are coplanar if they lie on the same plane, or vectors don't actually have a location, but if they're parallel to the same plane. So if you can find some plane where all three of these vectors are parallel to that same plane, they're coplanar, right? And if they're coplanar, the parallelepiped formed by those three vectors is going to be just a flat two-dimensional object. And so what's the volume going to be? Right, the volume is going to be 0. So if three vectors are coplanar, their volume, the scalar triple product, u dot v cross w, will be 0 because that's the volume of the parallelepiped. And so that's how you check that three vectors are coplanar. So let's show the vectors 1, 2, 3, 4, 5, 6, and 7, 8, 9 are coplanar. Well, what we're going to do is we're going to take the scalar triple product and show it 0. Okay, so we're going to take our determinant. I'm going to go through this really quickly, but remember to do your plus minus plus so we don't forget. Otherwise, you're not going to get the right answer. So we get plus 1, cross out the row and column containing 1, multiplied by the determinant of 5, 6, 8, 9. So then minus, take the next guy on the top, 2, cross out the row and column, multiplied by the determinant of 4, 6, 7, 9. And then plus 3, cross out the row and column, times the determinant 1, 2, sorry, nope, sorry, 4, 5, 7, 8. And super quickly, so the determinant of 5, 6, 8, 9, so 5 times 9 is 45, 6 times 8 is 48. So 45 minus 48 is -3. The determinant of 4, 6, 7, 9 is 36 minus 42. So 36 minus 42 is -6. And then determinant of 4, 5, 7, 8 is 32 minus 35. So we get 1 times -3, which is -3, minus 2 times -6, so that's plus 12, plus 3 times -3, minus 9, and we do indeed get 0. So the scalar triple product is 0, so they're coplanar. And that's what you're most often going to use the scalar triple product for. Okay. Any questions about any of the stuff today? Okay, so cool. So we'll pick up the talking about planes next week. And yeah, have a great weekend. Don't lose all your money on stonks. And yeah, I will see you guys on Monday.
Thank you.